All right, cool. Let's get started. So this is the last task that I want you to do for week number 6. In this case, this lesson is an introduction to some of the organic chemistry techniques. It's in 2 parts. So this is part 1, and part 1 relates into what we've just previously been talking about in regards to ketones and aldehydes. With it, we'll also be able to start talking about another functional group, which is the carboxylic acids. So success criteria, you should be able to do the same sort of naming conventions and properties. In this case, in the context of carboxylic acids, you should also know reduction reactions with the aldehydes and ketones, and then we should start talking about techniques today. Cool. So I will switch to the board notes, or I should say the document camera, to talk about some of these different techniques. So the first one we're talking about is making a ketone. And when we're making a ketone, I now need to start introducing some equipment. This equipment here is known as reflux. So that's the reflux setup. With this reflux setup, some things to note of importance is the first thing is that we have a little Bunsen burner there, and that's heat. And that heat's important because that, like we talk about in level 1 science, is increasing that rate of reaction. And that's because the heat allows those particles to move faster and then collide and react. In this solution here with my ketone, I have to remember that I'm starting with a secondary alcohol. Remember, the primary alcohol would be used for making aldehydes and carboxylic acids. The tertiary won't react, so we are starting with a secondary. This is also an oxidation reaction. So I would need an oxidant for that reaction to occur, say, for example, dichromate or permanganate. We need to do it in reflux. This is what a reflux setup looks like. So what we have is a flask, and we have a condensing tube. The main thing about a reflux condensing tube is that it will have a little stopper, so there's no escape of the liquids. So what is great about using this equipment is, first off, we are speeding up that rate of reaction because of the heat, but the problem with the heat is that it's going to cause things to evaporate. The condensing tube here and that reflux setup prevents things from escaping. Of the reactants / products. So it adds like a little stopper. So we have to remember with that heat, it causes things to, remember heat causes things to evaporate. And so that helps prevent that evaporation, or not evaporation, it helps prevent the loss of those vapors. Cool. The other thing that happens with the reflux tube is we have this condenser, and you notice how it says water in and water out. So what is happening is we have a little tube here, but we have like an outer layer of cold water that's flowing around the outside of the tube. And what that's providing is that cold water. And that cold water is useful because it means that we condense the vapors back into our flask. So that condenser is there to cool the vapors. So that way it returns to the flask. Now, when it returns to that flask, it can then react. So the other thing that is really great about using a reflux tube, and you'll see this in multiple reactions, not just with ketones, is that it ensures all reaction. So it makes sure that you ensures 100% reaction. Or like maximum yield, the other way you can describe it. Cool. And then the last thing you would do then after I was finished with that reaction is I would do distillation. That distillation is a purification process. And I'll show you distillation actually in our next example with our aldehydes. Cool. So as a refresher to that primary alcohol oxidation, we have to remember there's two steps. The first one produces the aldehyde, and the second step of that oxidation produces the carboxylic acid. So when I do this, or when I want to produce an aldehyde, I need to make sure I remove it, because if I don't remove it, it's going to oxidize again to the carboxylic acid, which I may not want. So we have to use, again, equipment set up for that to happen, which is known as a distillator. And you're going to freeze again, aren't you? I think my computer's just struggling. All right, we're just going to task manager that again. Cool. Now you can see it. All right, so here is distillation. I'm just going to write distillation down so that way we know we're dealing with a different setup. But what you'll see is some similar things that the reflux has. So we can see again that we have a flask, we have a heat source, we have the condenser as well. But what makes this different is that instead of having a stopper and then it just condenses back down into the flask, we have our condenser hooked up to a collecting flask. So similar things are happening. I'm heating that reaction to make it go faster. Obviously, it's going to evaporate. Now, in this case, when it evaporates, it's going to go down into the condenser, but that condenser, again, that cold water is flowing on the outside to help cool it down. But when that solution condenses, it's going to condense in a new flask. So vapors condense in a new flask. And so that's something that we can use as a separation technique and as a purification technique. So if you remember in the ketone notes that I was writing, I said then you'd purify, you're using distillation. This is distillation. With the aldehyde, however, the reason why I want to use this distillation setup from the beginning is because I want to remove the aldehyde from the solution. So what this has as a really important step is a thermometer. And I can use that thermometer to know when things will come off. So if I know the boiling point of the aldehyde, I can make sure that I heat it to that temperature and it removes from the reaction so that way it doesn't get oxidized as the second step. So you're basically removing to prevent the second oxidation to the carboxylic acid. And so that's why that thermometer is really important. The aldehyde also will be the first thing to boil off, and that's because it has the lowest boiling point of it. So if I was thinking about the list of stuff that's in that flask, you have things such as the alcohol, you have the alcohol, you have your oxidant, and you have water, because the water is usually used to just dissolve things. So these are your reactants. Then I will be producing an aldehyde. That's your product. So when I'm looking at that list there, the one with the lowest boiling point is the aldehyde. And so that's how it's being separated out. Remember that the alcohol and the water can do the hydrogen bonding, so it's going to have a higher boiling point. If there is any carboxylic acid that happens to be produced, it will have a higher boiling point than the aldehyde because, again, it can do those hydrogen bonds. So that's how that's able then to remove the aldehyde. And like I said, importantly, preventing that second oxidation step. Cool. And so logically speaking then, if I wanted to make carboxylic acid instead of an aldehyde, we're going back to that reflux tube. And we can either use an aldehyde or primary alcohol for making that carboxylic acid. And the reason why we're using that reflux tube is, again, to ensure that 100% reaction. In this case, I'm not trying to remove the aldehyde, so that's why the distillator isn't being used. And again, same sort of process. We're using the reflux in order to ensure maximum yield because everything's going to come back into that solution or into that flask. And we would end all of our steps with distillation because distillation is the final process. It's just used as a final purification step. It's a really specific type of purification step because you are using boiling point to separate. Cool, and then I'll use this as a jumping ground to talk about carboxylic acids because that's another functional group you have to learn. You learned this one last year. This case, what you have is the carbonyl with the OH. Remember that these properties are separate from the ketones and aldehydes and the alcohol. So even though it does have an alcohol and it has a carbonyl, it's its own separate category with its own separate properties. So make sure you keep them separate. The suffix change is oic acid. So you just remove the ending. Cool. These guys are very soluble in water, and that's because it can dissociate and lose that hydrogen ion and make that salt, and that can then dissolve into water. It also then has those acidic properties because it's a proton donor. I won't read all those out, but the main thing is these guys have higher melting and boiling points compared to the other hydrocarbons because of the ability for it to donate that hydrogen ion and mix in with the water. Oh, sorry, what was I saying? Higher melting and boiling points because the hydrogen bonds. Sorry, that's what I meant to say. And these guys are a weak acid. We'll come back to these in the ocean acidification essay that you guys write. Cool. Since it is an acid, it will turn litmus paper red. So blue litmus paper red or universal indicator red. That's also a very good way to identify it. Remember, this is unique to the carboxylic acids. This won't happen with the ketones, aldehydes, or alcohols. So specifically, carboxylic acids will be the ones to change litmus. These guys can conduct electricity because it's able to produce ions. It reacts with metals, but it's going to be a slow reaction. And again, it's because of the acidic properties. It will be neutralized in bases. It can react with carbonates to make salts, and you'll see carbon dioxide bubbles come off of it. Cool, I think that's the main things for those. And then the last thing is some naming practice just to kind of get you guys going with that. Hopefully that works again. There we go. Nope, there we go. Cool, so the thing to remember with this is that the numbering starts with the carboxylic acid. It has to be carbon number 1, and then that's 2. So that would be ethanoic acid. In this case, 1, 2, 3, 4, butanoic acid. So just keep in mind that when you are naming them, the carboxylic acid has to be 1. So in this case, that has to be 1, 2, 3, 4, 5, 6. So this methyl here is on carbon number 3. Numbering it only once, so it makes your numbering decisions very easy because this has to be carbon number 1. That would be 3-methyl hexanoic acid. This one here, we have 2 functional groups, but again, the rule has to go with the carboxylic acid being carbon number 1. So I have whatever the chlorine's going to get is going to get. I know you try to give the function groups the lowest number possible, but in this case, if it's a choice between the carboxylic acid and the chlorine, the carboxylic acid gets the lowest number, which is 1. This here is my methyl, and that's on carbon number 2. That is a ethyl, and that's on carbon number 4. And then this is my chlorine, which is on carbon number 6. Remember, you are putting them into alphabetical order, so that would be 6-chloro, 4-ethyl, 2-methyl, octanoic acid. And that's the name of that one. So don't be thrown off. I see a common mistake is that people number the carboxylic acid twice because they're trying to get the chlorine a lower number, and then they go 1, 2, 3, and they call it a 3-chloro. That would be marked wrong. You can only number it once, and the number starts with the carboxylic acid. So it's a really kind of easy deciding factor. All right, cool. One last thing to kind of talk about then is the reduction of the ketones, aldehydes, and carboxylic acids. It's basically reversing it, and you're increasing the hydrogen content, so you're adding back those hydrogens. In order to do that, you need either lithium aluminium hydride or sodium borohydride. So these would be the 2 reagents that you would just memorize, and that's how you go backwards. And it's what you'd expect to happen. So ketones would be reduced back to a secondary alcohol because secondary alcohols are what make ketones. Carboxylic acids would first be reduced to an aldehyde and then be reduced again to a primary alcohol. And again, it makes sense in the sequence of events. Primary alcohols make aldehydes, aldehydes make carboxylic acids. Cool. So yeah, just be mindful if you see any reversing on a flow chart, then that's what you're using. All right, so that is today's lesson. So you should know some of the organic chemistry techniques. The 2 techniques you should have learned is the distillation and reflux. And you should also know carboxylic acids as well, and that new reduction. So we've done oxidation and reduction. So go ahead and go to the Mahi choice on the Google site, pick something to work on, and all the resources are on Google Classroom.